Very well. Hello, my name is Galen Pickett. This is a video that is a part of the Physics 151 Mechanics and Heat online course. So, I want to tell you a little bit, just enough to help you understand what's in the textbook about vector algebra. So, vector is a quantity that has got a magnitude and a direction. So here, I'm going to call that the vector A. It has a magnitude on my screen here of maybe, 2 inches. And it has a direction, which is about, I'm going to specify that as, say, 30 degrees above what I'm going to call the x-axis, and there's the y-axis. So a vector is a quantity that has got both a direction and a magnitude. So, taking a vector A, a vector B, and I'm just drawing them here on the screen, adding these two vectors together, that's one of the things you do in algebra. You can do that by first drawing A and then drawing B. So there's the vector A, there's the vector B. The resultant vector, which is the sum, goes from the beginning of A all the way to the end of B. There's the resultant vector C. I would write this algebraically as A plus B is the vector C. So there you go. There is no need to stop there. You could easily add many vectors together. So here is, say, V0. There is V2. There is V3. There's V4. Now, I drew them all sort of going across the screen to illustrate not just the geometric way to add vectors together, which is to draw these arrows, these magnitude and direction quantities from tip to tail to tip to tail to tip to tail. If I look at just what is the projection of each of these vectors along the x-axis, so this arrow tells me how far V1 goes in the x direction. This arrow tells me how far V2 goes in the x direction. This one tells me how far 3 goes in the x direction, and this tells me how far 4 goes in the x direction. So this is x0. X, well, I wrote it as 2, I'll keep it as a 2, x3, x4. So I could either say my total resultant vector, say W, is equal to V0 plus V2 plus V3 plus V4. That's just one way of saying I've got a quantity that has a magnitude and a direction is given by these magnitude and directions. I could also specify Wx, just the x component of that vector, is equal to, first, the x0 plus the x2 plus the x3 plus the x4. So, so there you go. Now, you could say to yourself, Dr. Pickett, why, I know how to count. You started with a 0, you went to a 2, 3, what happened to 1? There is a very important vector which I neglected to draw in there, V1, but it's a vector which doesn't take you anywhere. Here I've got V1 is the 0 vector. It has got 0 in its x component, 0 in its y component, 0 in its z component. And that's the notation that the book uses. That's the notation that we'll be using in this course. So I could just as well write this as plus x1, but x1 is the x component of this vector here, which is 0. So algebraically, adding the vectors together is either the same thing as writing one arrow, one arrow, one arrow, one arrow, or you can just do it component by component. So if I'm given A is equal to AX, AY, and AZ, and I'm given the components of B are equal to BX, BY, and BZ, then the sum A plus B I could just as well write as just AX plus BX for the x component, AY plus BY for the y component, AZ plus BZ for the z component. Or I could draw them. Both works just fine. That is so much for vector addition. So this is addition. That's one of the operations that goes into the vector algebra, addition. There is a multiplication. But it's not, at this point anyway, at this point in the course, it's not multiplying a vector by another vector. What I can do is take something which does not have a direction, so a scalar, and multiply it by a vector. This keeps the direction the same, but it changes the length. So let's take an example. I'm going to do this geometrically. Here's the vector A. I'm going to take the vector A and add it to itself. That is the way I would do it as a picture. This vector here, which I'm going to call B, which starts at the beginning of A, goes to the end of the second A. That's the vector B. What I've got is B is equal to A plus A. That's the same thing as 2A. So you can think of the 2 as being a shorthand for adding A and A together, or you can think of the 2 as something which takes my original A, keeps its direction the same, and just makes it twice as long. Maybe it doesn't surprise you that you could write C is equal to 1/2 A. So C would now be something which goes just in the same direction as A, but only half as long. And I think I can show to you that C plus C is equal to A. So if I take a vector that is half as long as A and add another vector that's half as long as A, I get something which is just as long as A. In other words, this is the same thing as 1/2 A plus 1/2 A is equal to A. And that is the sort of operation that you can freely do. So I've got addition and multiplication. Multiplication keeps the vector in the same direction, changes its length. There is one caveat when you multiply by -1. When you multiply by -1, what you get is, if A went in that direction, minus A points in the other direction. It's got the same magnitude as A, points in the opposite direction. So if I did A plus minus A, I get back this vector which is 0. So if I've got addition and subtraction, I've got this multiplication and vector addition, I can construct what I mean by subtracting vectors. And that's something that we're going to need to do a lot in this class, because this class is about how quantities change, how the position of an object changes, how its momentum changes, if its velocity changes, that will change where it will wind up. We want to explain all of that. That's the story of mechanics. So to subtract a vector, if I've got a vector A and a vector B, B minus A, well, I could handle this by doing a vector addition. I could add B plus a vector which is going in the opposite direction to A. So let's draw that. So I've got B, there's the B. The one that goes opposite the direction to A is that one. So there is B minus A. So there was, this one was B, here's the minus A. I could, so that is one way to do this. Another way to do this, notice that this vector here, the B minus A vector, the resultant, is the same as if I just started at A and went straight to B, drawing both of the vectors from the same common point. And that is something that you're going to want to get used to. This is the way, for instance, if I've got an object that starts at the origin and is changing its position at different times. So here is R at 1 second, R at 2 seconds, R at 3 seconds. So there is position vector R1, there's position vector R3. If I wanted to know what was the change in position in going from 3 to 1, well, that's the same thing as R3 minus R1. R3 minus R1 is the vector which takes me from where I was at 1 to where I'm going to be at 3. There is the delta R. The delta R is the thing which changes the position, and if I want to define an average velocity, the average going from 3 to 1, that's the same thing as R3 minus R1. that has units of meters, I then multiply a scalar multiply by 1 over how much time went by. 3 seconds minus 1 second. So I get a vector which is parallel to the delta r, and I need to know the rate is how far I go. That's the total displacement divided by how much time went by. And that's enough to get you started.